All right, so today, y'all, come on, let's get started. Today we are looking at ways to, the specific way to find enthalpy with calorimetry. We did stoichiometry for our last session, right, where we had an equation and it said, you know, this equation has this many kilojoules of delta H associated to it, and we had to figure out, well, if we only take part of one of the reactants or one of the products, how much would actually be released or absorbed. So you'd find moles and then mole bridge. So everyone good with the stoichiometry part? Okay. Today we're looking at the specific laboratory technique of calorimetry in order to find the delta H of a reaction. So before we can actually jump into using coffee cup calorimetry, we got to reintroduce ourselves to Q equals MCAT. Remember that? I think all of us, regardless of what Chem 1 class we took, we did Q equals MCAT, where Q is the amount of heat associated with a particular reaction. M is mass. When we get to coffee cup calorimetry, that mass has to be the total mass of reactants. But in the first problems we're going to do, it's just a mass of one substance. C is the specific heat in units of joules per gram degree Celsius. Okay? The specific heat of water, I'm going to need you to know, it's not on the sheet, it's 4.18 joules per gram degree Celsius. And this is liquid water. Steam and ice have their own specific heats. This is also an incredibly important conversion between joules and calories, which you'll get to in physics anyway. Yes? Nope. Nope, you will not need to know those. The question was, do you have to know the specific heat for ice and steam? And the answer is no. You will be given those if you need them. The mass of the solution is in grams, and if you notice, you have here the grams that can cancel. One thing that makes AP a little more tricky, and this is just something I want to mention, in your textbook and in some of the homework problems, they give you something called molar specific heat. And what that gives you is a unit of joules per mole degree Celsius. If you get a specific heat with a mole in it, what do you do differently? What do you put in instead of a mass of grams? You have to put in moles instead. That's not a hard concept, but it's going to trip you all up if you don't do your units, just like those of you who did not convert your torr to atmospheres on the last test. That's what's going to happen to you. So don't be afraid of it. Just always write down your units, and you will not have a problem. Okay? Don't be lazy, because it'll pay off in the end. And then your delta T is your change in temperature. And in this case, degrees Celsius. We'll talk about that in the next problem. All right? So what we're going to do now is just jump in and play with this equation for a little bit. How much heat must be added to change the temperature of 250 grams of water from 25 to 60 degrees Celsius? Since we're looking for heat, we use MCAT. All right, so Q is equal to, what is our mass? 250 grams. The specific heat? 4.18. Does anyone know what has the highest specific heat in the world? It's water. Yeah, 4.18 is a huge specific heat. All your metals are like 0.1, 0.3, that kind of thing. If you think about metals heat up very, very quickly and they cool very quickly compared to that of water. Does anyone know what happens if we didn't have such a high specific heat? Any consequences? Yeah. Yeah, we'd all, in the Texas heat, wouldn't take a lot of energy to pretty much, what our body is, what percentage of water? A really high percent, right? 70-something%. Yeah, we'd be toast. Not literally toast, but we would not be faring very well. Water's role is huge with its hydrogen bonding, which plays a role in the specific heat, tremendously important to life. So whenever we do our delta, it's always final minus initial. So final is 60, initial is 25. What if they gave me those in Kelvin? Yeah, it's the same thing. For those of you who are like, no, it's not, you need degrees Celsius. If we're looking at degrees Celsius and our say we're going from 0 to 100, what's our delta T here? 100, right? But if this were Kelvin, 273 to 373, what's our delta T? 100. So just know, I mean, they're not going to usually give you a Kelvin degree, but just know that since it's a difference, the scale is just, that difference will be the same regardless. So Q, we're going to go ahead and put a point here and make these all 2 sig figs. Q is the 2 sig figs, how many joules? 37,000 joules. Leave it in joules, folks. I get a lot of you who are like, well, I'm changing to kilojoules just because. That's just not smart. Why would you write down an answer and then change it just because and then potentially get it wrong? That's arrogant and it's not smart. So let's not do that. Look at what they ask for and just give you what they ask for, okay? In this case, they didn't specify, so leave it in joules. No reason to change it. If 2.09 joules are required to change the temperature of 15 grams of mercury by 1 degree Celsius, do you need water? You can get up and get water if you want. If 2.09 joules are required to change the temperature of 15 grams of mercury by 1 degree Celsius, calculate the specific heat of mercury. Well, the specific heat, we can sit there and plug into Q equals MCAT, and I'm fine with that, but let's talk about another way to do this because I love playing with units. Units are how I passed physics. We know that the units on specific heat, the true definition is joules per gram degree Celsius. In words, specific heat is how much energy is required to raise a gram 1 degree Celsius. So all you have to do is plug your stuff in here to find specific heat. Your joules divided by your grams divided by your degree Celsius. You don't have to use Q equals MCAT. You can. It's exactly mathematically the same thing, but I like, in a case like this, just to go 2.09 joules divided by 15.0 grams divided by 1 degree Celsius. And then to 3 sig figs, what is my specific heat? 0.139 joules per gram degree Celsius. So whatever, you could use MCAT too. I'm just trying to show you a different way to do it. So that's a really low specific heat. So the lower the specific heat, the faster and easier the heat moves. And if you've had me last year, you've already heard this, but how many of you have helped make Thanksgiving or Christmas dinner at home? Okay, so have you ever been the one to take out the turkey or the ham out of the oven? Has no one ever taken? Okay, you have. Okay, man, I'm gonna make y'all I'm gonna make y'all do like life skills. I'm gonna make you make beds with hospital corners. I'm gonna make you take out turkeys from ovens. Anyway, point being, since you're the only one, apparently Jacob, that knows this, have you noticed how hot the pan was versus the aluminum foil? Like how quickly you could touch the aluminum foil? It's because aluminum foil has such a low specific heat compared to the steel whatever alloy of the pan. Okay? So the lower the specific heat, the faster that actually moves. Okay? Can we have a negative specific heat? No? No, we can't. But it would be amazing. Because, let's talk about it. What does it mean to have a negative specific heat? And I talked about this last year. If we put heat into it, it cools off. If we take heat away from it, it heats up. So imagine we have a house, right? And if we were to cover it with a whole bunch of negative specific heat stuff in the summer, as the sun beats down on it, what would be happening? It would cool off. Isn't that amazing? Then if it were freezing outside, it would be nice and warm inside. Not going to happen, but if you all end up figuring out a way to produce something like that, you could run for president. Wrong. Wrong. Yeah, it was great. Last night was a great debate. Okay. I'm basically putting a timestamp on this video, so when I don't redo videos last year, we'll know who our president is this time next year. Okay, yeah, moving on. Everyone get how to solve this? Yeah, okay. I'm going to have to change that metaphor that I've used for 15 years. Yeah, I know. Trumping zeros totally can't be used anymore. I'm going to have to come up with a different millionaire. Who can we use? Oprah? Done. Can someone draw me an Oprah? This is Trump. This is Donald Trump, and I used him in an analogy like well before he ever ran for president. This has been here since like 2000, a really long time, because he's been around a really long time, and I get that, but just not in the White House. So anyway, so I need a new Oprah. If anyone wants to draw me an Oprah. When I write recommendations for you people, that's the things you do. You give your teachers nice things. An Oprah hand-drawn to match my characters would be great. Okay. All right. Is there someone who's, like Dell? Who else is? Draw me an Oprah. Thanks. And can you color it, too, with pencils? Yes. Is she? Okay, and then we'll laminate her, and we'll add her, and we'll take Trump, and we'll have a ceremony. Well, I wonder if I should wait, because if he becomes president, I guess I could leave him up there. Yeah? Okay, there's no rush. This will be a plan, but yeah, anytime, and then whoever, and we can have multiple Oprahs. I don't care. All Oprahs? Okay, but what do I say? We can't. I use trumping it. Oprah it doesn't sound as good as trumpet. Sorry, people at home. You can just keep fast forwarding. Yes. Oh, that's good. You get an O and you get an O. There you go. Okay, good. This Oprah thing's working out. I like it. Like it a lot. All right, number 6. I apologize to people at home, but whatever, you're getting a lesson and you're not here, so that's just tough. Calculate the final temperature after 1,575 joules of heat are removed from 85 grams of a sample of ethyl alcohol, originally at 23.5. This you have to be careful because of what they're saying with the verbiage. Heat is removed from a sample of ethyl alcohol. So heat is leaving the system. So what is the sign on that heat? Negative. That's the kind of thing you got to watch out for. So again, I'm using Q equals MCAT here. My mass of sample is 85.0 grams. My specific heat of the sample of ethanol, it's not 4.18. It's 2.4 joules per gram degree Celsius. And my final temperature, what are we solving for? Calculate the final temperature. So you can do one of two things. You can just write delta T down, find out what the delta T is, and solve. I kind of just like to set it up all in one swoop. Now here's the thing, folks. I see students do this, and they start to distribute that thing. I'm like, what are you doing? No. To solve, all you do is take 1575 divided by 85 divided by 2.4, and then you add 23.5. Don't distribute. That's crazy. Math is hard, but if you do that, you're making it way hard. So what's the final temperature of this? It's 15 point something. I just don't remember what the point was. 15.8. 15.8 degrees Celsius, which makes sense. Okay? Because heat was removed from the substance, so the temperature, wait, it went down. Yeah, heat left the substance, so the temperature of the substance dropped. Okay. Number 7 is an example of a type of problem that is very common, and you're going to do it in physics a lot, and that is taking something hot and throwing it into some water and then doing stuff with it. So the concept behind that, if you take something really hot and you throw it into cold water, what happens to the heat? It moves from the hot thing to the water. What's the relationship between the magnitude of the heat that goes from the, it's the same. So what we're actually saying in a problem like this is Q lost is equal to Q gained. Okay? So if Q loss is equal to Q gained, I'm just going to use MCAT twice, one for the heat, one for the lead or whatever metal, and one for the water. But when we lose something, our heat is negative, right? And when we gain something, it's positive. So even though these heats are equally, the magnitude is equal, they're going to have opposite signs, so you have to make one of them negative. Technically, you can make either side negative. It doesn't matter. I just like being consistent. The lost, I put the negative, and I do the metal. And the gained, I do the water, because that's what's gaining the heat. So everything on the left is about the metal. So what's the mass of the metal? 28.4 grams. Heated to 100, what's the specific heat of the metal? That's what we're looking for. Change in temperature of the metal. Final temperature. Yeah. Why do they have the same final temperature? Yeah, once the heat's transferred, we reach an equilibrium, a temperature at the equilibrium occurs, and we're at the same temperature. So we heated up that metal initially, to 110. That's about the metal. The mass of the water is 100. Put a point there to make it 366, please. The specific heat of water, 4.18 joules per gram degree Celsius. And then I always run out of room on this problem. Our final temperature is 25.34 minus the original temperature of, whoa, how come the metal changed like almost over 100, 70-something degrees, and then the water only changed a degree? Yeah, the specific heat of water is a lot higher, so it's not going to experience as much of a temperature change. So go ahead and solve for C, and just give me 366. Yep, 0.129 joules per gram degree Celsius. Trying not to. All right, does everyone get that? So you're going to get problems like this. A more common problem, which you'll get on your homework, which you're going to not like the math, is solving for the final temperature. And if you're solving for the final temperature, you're going to have it on two sides of the equation, the variable, TF. Then you will have to do some distributing and moving stuff around and solving. It's nothing that's not algebra-based, so you can handle it. But yeah, it will take some time. And you have to just turn on the TV, sit down, and do some math. You'll get it done, okay? All right, questions? Okay, now we're going to run into, I'm going to do a little lesson here on multiple choice questions on the AP exam. We're being nice to you right now because we're trying to get you used to the rigor of AP, but on the AP exam, you do not get your calculator for the multiple choice part. You will be expected to do math, but I write 5 multiple choice questions, AP questions, and send them in pretty much every month, and I never know which ones they're going to use. They don't release multiple choice questions, so I never really see what they're going to put on there, so I'm not at an advantage. But my advantage is I know how to write them. And so I know for a fact when I write these questions, I have to make the math easy. It has to be numbers that round, or it needs to be a problem that looks like you have to do a lot of math, but you can actually rationalize through with not even touching your calculator. And these are examples of this. A lot of you, if I were to give you that, would start doing MCAT equals MCAT and start doing a whole bunch of solving, and you're going to run out of time on the multiple choice part of the exam because you didn't need to do that much work. So let's talk about it without using a calculator. A 100-gram sample of water at 90 degrees Celsius is added to a 100-gram sample of water at 100. So we have equal masses of water, and water and water have the same specific heat, right? So What do you think we can do that's really easy? Average the temperature. So what's the answer? 50. Did we not? We didn't even touch a calculator. Okay? This is a legit possibility of what could show up. I promise some students will be plugging things in, putting 4.184 in, and trying to solve for final temperature. Insanity. Okay? Don't do it. So this next one. A 100-gram sample of water at 90 degrees Celsius is added to a 500-gram sample of water at 10 degrees Celsius. So we have a lot more of the cold water, so we know it can't be the average of the two. So what are our options? It's C. Why is it C, Rui?
Well, because there's more of the cold, and because they have the same specific heat, it's going to lean more to the colder area.
Exactly. And that's why the questions are written this way. We're giving you a range. We're not expecting you to solve for the exact value. But even if it were, if your answers were 85, 70, 50, and 15, you choose the 15, right? Because we know it has to be colder than the average. Y'all getting it? All right. Okay. You have a styrofoam cup with 50 grams of water at 10 degrees Celsius, and you add 50 grams of an iron ball at 90 degrees Celsius, and they give you the specific heats. The final temperature. Well, we're dealing with the same masses, but water-specific heat is way higher, right? So where's the temperature going to be closer to? Water's temperature. Is it going to be an average temperature? No. So it can't be this. So it has to be the one closer to the water's temperature, which is C. All right? Does everyone kind of get it? So I need you to, I'm trying to figure out ways to help you with multiple choice and with time. When you're running out of time on the AP, it's because you're doing things the long way. So we got to get fast. Because again, when I write the questions, I will purposely say, oh, 40 grams of sodium hydroxide, da-da-da-da-da, and you have to find moles. Well, guess what? The molar mass of sodium hydroxide is 40, 1 mole. Like, they're supposed to be easy calculations. Okay, so now let's get into the crux of why we're talking about all this. That's because we're going to be doing coffee cup calorimetry. On your calendar for the weekend, in case I forget to mention this tomorrow, it says something about homework, whatever, and then pre-lab, and then under it is a statement that says, no pre-lab, bring your lab book. It's no pre-lab, bring your lab book. You don't have a pre-lab for homework, okay? Your only homework will be the normal homework assignment. So what we're doing on Monday and Tuesday is you're writing up lab procedures for calorimetry. And we're going to do a lot of number crunching, and we're going to figure out some things. When we do a reaction, and we put a reactant and then a reactant together, it's either going to be endo or exothermic normally. And let's pretend it's exothermic. If this reaction is exothermic, heat from the reaction is going to go to the thermometer. Also, we're using a styrofoam cup, but usually styrofoam cups can't even hold in all the heat. Heat's going to get lost normally. And so what's different about AP than what you did in Chem 1 when you did some of these problems is now we have to take into account that sometimes heat leaves as well. And so when we do problems, we've got to first decide, is heat leaving? If so, it's going to make our math a little bit more intense. It's not hard. You just need to recognize that. So what we're going to do is use Q equals MCAT to figure out how much heat went to the thermometer, and then something else which I'll show you for heat that actually leaves. Remember I was talking about that molar heat capacity? We'll talk about that in a minute. All right, let's just do this problem. This isn't easier. This would be a Chem 1 problem. We have a coffee cup calorimeter. So when you see coffee cup calorimeter, I immediately want you to think Q equals MCAT, because that's always what you do to solve for coffee cup calorimetry problems. You have 1 gram of sodium hydroxide dissolved in 150 grams of water. They give you the 2 temperatures. What you're going to do in the lab is mix a certain amount, and you have to find the 2 temperatures. Then you're going to take that information and solve for Q. Now let's look at this reaction. It says calculate the heat liberated. What is that telling us? What does that mean? We need to make sure this is exothermic. So I'm going to predict we got to have an exothermic thing, and we're going to have an issue, which I'll talk about. All right, so Q equals MCAT. We are now going to go ahead and start plugging stuff in. We're solving for Q. The mass has to be the total mass of both reactants. Notice they gave us the mass of water. Sometimes they just give you the moles of water. If it's not at room temperature, they'll tell you the density. What's the density of water at room temperature, though? 1 gram per mil. So you can make that assumption unless they give you a different density, and then you'll have to find how many grams. So we have 1.095 plus 150, so it's 151.095 grams of reactant. Now, we have a solution here. It's not water now. It's got a different specific heat. But what did they say? Assume the specific heat of the solution is the same as that of water. It takes a lot of solvent to kind of change that, so most of the time they'll just say assume. So that's going to be 4.18 joules per gram degrees Celsius. You can also think of it this way. The sodium hydroxide is changing that solvent, which is water's ability to absorb, so we're really measuring water's change in temperature. But anyway, not important. All right. So now you've got to do final minus initial. What's the final temperature? And the initial temperature? All right, so final minus initial like always. So let's go ahead and solve for Q. Give me 4 sig figs. We're not going to use the specific heat to determine sig figs. That's two. You mean 11,450? 150. Oh, I thought you said 450. Okay, 1,150. How do you do 4 sig figs? Is it 1,140 something? So 50 with a decimal. All right, so that's how many joules of heat. Does anybody see a problem though? It's positive. Uh-oh. What's going on? Well, when you do coffee cup calorimetry and you use a thermometer, what we're actually recording here is the energy that went into the thermometer. What did the thermometer do with the heat? It absorbed it. So we're looking at it from the perspective of the thermometer. So in the world of AP, they have this little statement that says, well, the heat of the reaction is actually equal to the negative Q when we do calorimetry. So we always have to do a sign change. I need you to show this and then give me that delta H. AP graders want to see, you know, that it's not just magically changing the sign. There's a reason. So our actual delta H of the reaction is equal to negative 1150 joules. Does that kind of make sense? So anytime you use a thermometer, you're always going to have to change that sign because we're looking at it from the perspective. The system's different. The system was actually the thermometer when we did Q equals MCAT. Okay? We need to look at it from the perspective of its surroundings, which is the solution. Okay, are you ready now to get a harder one? Yeah, let's do it. No, wait, I forgot. I need to add to this. We're going to make this a part B because I'm going to make your life. It seems like I'm making it harder, but at the end of the day, you're going to want to know how to do this. We're going to add a part B to this. Do you hear the coughing? Calculate the heat released per mole of NaOH. So to make that number more meaningful, this is really just us figuring out how much heat sodium hydroxide gives off when it dissolves. Do you see that? That's all we're really doing is dissolving sodium hydroxide. So a lot of times people want it reported per mole of whatever we're dissolving. It's like the heat of dissolution, what we call it. Heat of dissolving. So that, to be meaningful and to be something we can apply to any situation, we got to do it per mole. So what do you think you do? It's as easy as it seems. What do you think you do? Moles of what? Right. Do we have moles of sodium hydroxide? Nope, but we're going to calculate it. So it is the 1.095 grams of NaOH. We're going to convert that to moles. There's 40. I make sodium hydroxide all the time, so I know that's 40 grams per every 1 mole of sodium hydroxide. So how many moles of NaOH do we have? Just give me 3. Thanks. 0.0274 moles of NaOH. So then I just take the heat per mole and to 3 sig figs, how many joules per mole do I get? Let's do it in scientific notation because it's going to be a huge number. Let's just do 3. Times 10 to the 4th, so it's not that huge, but 42,000. Negative 42,000 joules per mole of sodium hydroxide. You don't have to write of sodium hydroxide, but I just wanted to make it clear. So if we ask you per mole of substance, per mole of a reactant, that's what you need to do. All right, last problem, and this is the penultimate we're going to do because you're going to see some things that you didn't have to deal with in the last problem. It says a 50-gram sample of 0.2 molar sodium bromide, they have the initial temperature, is added to a coffee cup calorimeter containing 50 grams of silver nitrate. If the heat capacity of the calorimeter is 65 joules per degree Celsius and the specific heat of the solution is 4.2 and the final temperature is 25.4, calculate the heat released in the reaction. Y'all need to watch the video. This is probably the most important problem all day, okay? All right, so good luck. Q equals MCAT is going to solve for the temperature going to the thermometer. How do I know that heat is also leaving the calorimeter? A couple things in here are clues. Do they say assume no heat is lost? Okay, do you see that? They don't say assume no heat is lost. So heat is leaving and heat is going to the thermometer. Another thing is they give you the heat capacity of the calorimeter. That's how much heat per degree Celsius is leaving anytime that happens, all right? So we'll tackle that second. This is always a two-step problem. So we're going to solve Q equals MCAT here, and then we're going to solve for the calorimeter there, and then we'll add up those two heats, okay? So let's just do the easy part first. Q equals, what is the total mass of my solution? 100 grams. The specific heat of the solution, is it water? No, they said it was 4.2 joules per gram degree Celsius. My final temperature? Let's just go ahead and give me delta T straight up so I can save space on the board. Is this 1.75? 1.75 degrees Celsius. All right, so let's go ahead and give me a whole number because I think there's enough sig figs of how many joules go to the thermometer. So this is to the thermometer. $735 joules. Okay, now, because they don't say assume no heat is lost, we have to assume heat is lost. And we use a cute little equation called Q equals CAT with a capital C. You don't have to memorize that. All you need to do is look at the heat capacity. Whoa, up here. I need to figure out how many joules are leaving. What do I have to do mathematically to this to just get joules? Look at your units. Multiply by temperature. And that's what this is. The 65.0 times the same change in temperature. We know how much is leaving per degree, so how many is leaving per 1.75 degrees? So 65.0 joules per degree Celsius times the same delta T. So how much heat is leaving the calorimeter?
So 114.
114 joules leaves. All right. So to get our total, we look at the heat that went to the thermometer plus the heat that left, right? So RQ is equal to 735 plus 114. So how many joules? 849 joules. Are we done? Have we found delta H yet? No, because look, this thing says calculate the heat released, right? We should be getting an exothermic value. So we still need to do the negative. We always have to do that. We always have to say that delta H is equal to negative Q. So delta H is equal to negative 849 joules. Do not flip the sign before you add them up. Because if you would have said, oh, it's exothermic, made this negative, and then just added that as a positive value to that, you see how you would have got the wrong answer? So you either need to make them both negative and add them. I say wait until you're done, and then at the end, change the signs. So did we need all that 0.2 molar stuff? Sometimes in AP problems, they give you extraneous information. Now, if this problem then had a part B and said, calculate the heat released per mole of sodium bromide, then yeah, you would need the molarity in order to figure out, assuming a density of 1, in order to figure out the actual moles. So sometimes you need it, sometimes you don't. So don't assume that just because it's written there, you have to actually use it. Any questions? So practice this homework's important. Coffee cup calorimetry is important. Okay? So tomorrow we do the flippy thing with our heat of formation equations. So that'll be fun. All right, that's it. Have a good day.